present a window. Select window or screen, slides, allow. Very good. So the Tip5 hash function for recursive Starks. This is a paper written jointly by myself and 4 co-authors, Alexander Lemons, Jan Ferdinand Sauer, Bobbin Threadbare, and Al Kindi. You are listening to the voice of Alan Shipyenyats. And if you look at the paper, you will notice that Al Kindi's name is not on there, and that's because I did not get around to uploading the most recent version yet. So, why do we need a new hash function? That's the first question I'll be addressing. And then I'll try to explain what I had in mind while designing this hash function. Then we see concretely how it's built up, and finally I'll give some numbers to wrap things up with. The entire motivation of this exercise in hash function design is Starks, in which case we want to build Merkle trees, and we need to build some more Merkle trees, and we need to do the Fiat-Shamir transform, and then we need to build some more Merkle trees. The key takeaway is that we need to do a lot of hashing. And so we want to have fast hash function. And particularly in a recursive Stark proof, where we prove the correct verification of a Stark verifier, that hash function needs to be proven to have been evaluated correctly over and over and over again. And so, yeah, we need to prove the correct evaluation of that hash function. And in order to prove that, the hash function has to have nice arithmetization properties. So we can't use Ketchak, we can't use Blake 3, we can't use SHA-256, because those hash functions, they are secure, but they were not designed with arithmetization in mind. And there are functions that were designed with arithmetization in mind, like MIMC, Rescue Prime, Poseidon, Reinforced Concrete even is somewhat arithmetizable. The interesting thing about Reinforced Concrete is that it's handily the fastest of the selection, and it's because it uses a lookup gate, or several lookup gates. And I like that principle. Lookup gates strike me as a robust way to thwart algebraic attacks. There are a couple of points, though, that I didn't really like about Reinforced Concrete. First and foremost, being that it didn't work over the field that we are interested in. And secondly, there's only one round where lookups happen, and I like my rounds to be uniform. With respect to the others, they're all slow. They're all slow. Okay, so the field is some people call it the Goldilocks field. I think that's a misnomer, because the Goldilocks field is obviously 2 to the 448 minus 2 to the 224 minus 1. But this prime modulus has a similar structure. You could call it Goldilocks minus minus. We refer to it as Oxfoy after the hexadecimal representation, but we also call it the B field. B stands for base, because we also have an X field where X stands for extension. This field is awesome because every field element fits into a U64. The product of any two U32s fits in this field. And this field is good for number theoretic transforms. And we're not the only guys using it. I think Polygon 0, back then they were Mir, perhaps. They were the first to use it, I think, and since then it has spread around. We want every round to be the same because we're going to be arithmetizing this in a algebraic intermediate representation where we have cycles, and in every cycle a state is updated according to similar rules. So it has to be easily arithmetized, and we want the number of rounds to be small because every round corresponds to one cycle, and so the way we're arithmetizing this in Triton VM is there's a hash coprocessor. So whenever the processor wants to hash something, it sends data to the hash coprocessor. The hash coprocessor computes the hash and sends it back. From the processor's point of view, only one cycle has passed, but from the hash coprocessors, the number of cycles has passed that corresponds to the number of rounds in the hash function. And so the number of cycles in the hash coprocessor is num rounds times number of hash invocations. And it's possible that this hash coprocessor actually determines the total number of rows in the entire execution trace. And so that's why we want to have as few number of rounds as possible so that we get a short execution trace. It's also nice to have a small number of rounds for speed, but it's possible to get fast hash functions that still has a large number of rounds if those rounds are very, very light. It has to support efficient building of Merkle trees because that's what most of the hashing is used for. And so we need to do a fast way, an efficient support for merging two digests into one. And the way to do that is to use a wide sponge state. Well, there may be other ways, but this is our strategy. So this is the sponge construction, which you can instantiate with any pseudo-random permutation. And in fact, this is slightly different from the sponge construction because this is a sponge construction in overwrite mode. So whenever you absorb data, those are the first three iterations. In fact, you just overwrite the top 10 field elements instead of adding the data block into those field elements. I did not verify the proof of equivalence for the sponge construction in full generality, but certainly when it comes to pre-image search, second pre-image search, and collision search, the two constructions are equivalent. And in this case, we also see two instances of squeezing. So this is technically not the hash function, but the sponge construction. The hash function is defined as having only one squeezing iteration. The important takeaway here is that you can instantiate a sponge construction from any permutation, from any pseudo-random permutation, excuse me. And so the question is, what does that permutation look like? That's what we're getting here. This is it. It has 5 identical rounds, starting with a layer of S boxes, followed by an MDS linear layer, followed by an injection of constants. And the constants that are being added, those are the only things that are different in every round. Now, there are 2 types of S boxes. The first 4 S boxes are split and lookup S boxes, which we'll get to later. And then the next 12 S boxes are plain old raised to the power alpha, where alpha is the smallest exponent whose power map is invertible, which for this field is 7. That's it. Okay, so what does one round look like? Well, the easy part is adding constants. Then we have an MDS matrix, which we'll get to later, or which I'll get to in more detail later. Then we have the simple S boxes. That's the power map I just mentioned. And then there is this split and lookup S box. And the idea here is that we're going to take the bytes. So remember, every field element consists of roughly 8 bytes, and we're just going to take the raw bytes, interpret those raw bytes as field elements in the field with 257 elements. And we're going to add 1 cube and subtract 1. That gives us another byte, and then we can recompose those bytes again, thereby giving a new field element. And if you're wondering whether this is a permutation, yes, it absolutely is. And the reason why is because this permutation, and it has to do with the formula in the middle, that x plus 1 cubed minus 1, it sends the number p to p, numbers that are greater than p, to numbers that are greater than p, and numbers that are smaller than p, to numbers that are smaller than p. And so if you only plug in valid field elements, you're guaranteed to see only valid field elements at the output side. Most of the performance gain that justifies including Al, the last co-author, comes from Clover Algebra related to computing the MBS matrix vector multiplication. So following polygon 0, we have a circulant MDS matrix, and we want to compute that matrix vector product over the integers so that we can avoid doing modular reduction, right? So one standard way of computing a circulant matrix times vector product is by taking the first column and the vector and transforming both to the frequency domain using the NTT, computing the Hadamard multiplication there and transforming them back. But we don't want to do this because that would involve computing many modular reductions, and those are expensive. So we want to avoid the modular reductions, and in order to do that, we're going to compute the product over the integers instead. That kind of nullifies the whole point of the NTT, and that's true. We're going to apply another technique from the NTT. So remember that a circulant matrix times vector product can be equivalently described as a product of two polynomials modulo the cyclotomic, well, this is not the cyclotomic polynomial, but the cyclotomic polynomial is a divisor. This is x to the n minus 1, where n is the number of coefficients in your polynomials. This is the height and width of the matrix. And so by choosing a circulant matrix, we can actually compute the matrix times vector product using polynomial algebra instead. Now, the nice thing about this modulus x to the 16 minus 1 is that it actually factorizes. And two factors are x to the 8 plus 1 and x to the 8 minus 1. And so we can actually compute the product on the first line if we have the products on the next two lines. And for the line in the middle, unfortunately, the best we can do is Karatsuba, because remember, we're still working over the integers. We can do better if we are allowed to use primitive roots of unity over the field, but we're not allowed to use that. That's the whole point. And for the second line, for the bottom line, the modulus actually has the same shape as the modulus on the first one. It's just that the degree has halved. And so we can apply the same decomposition. X to the 8 minus 1 factorizes as x to the 4 plus 1 times x to the 4 minus 1. And so once again, we can apply Karatsuba, and we can recurse on the bottom one again and again. And in practice, you want to stop before you hit x to the 1 minus 1. But that early abort is a matter of tweaking the parameters, and I'm not even sure that it will be the same for every machine architecture. Okay, so here are some performance numbers. All these numbers were obtained on my machine, which is in fact the machine I'm presenting from, where we implemented Rescue Prime Optimized, Poseidon, and Tip5. And Tip5 is handily the fastest by almost a factor of 10 relative to Poseidon. But we don't just care about the speed of the hash function. What we care about is the speed of the Stark prover as it proves the correct verification of a Stark proof. And so we have to take into account the larger number of entities that the prover has to do, the larger number of rows that it has to compress before it can start Merkleizing. The larger rows, right? Because the number of columns is larger. All those things make the prover slower, but in exchange, you get a faster hash function. And after you do all that maths, you would expect a factor 2.68 speed up in Triton VM, which is great, which totally justifies switching to Tip5, which we have since done. And since that switch, we have noticed a speed up in excess of this number. There are reasons why it's not quite an apples to apples comparison, but the actual number is in excess of 3. We are confident. So yeah, we can the entire story reduced to a short sentence is we have a new hash function that gets us almost a factor 3 faster prover in Triton VM. That's the presentation, and I'm open for questions now.
Alan, I had a question about this cascade table.
Hang on, let me open the paper so I can look at what you're looking at.
I guess it's page 12, 11 to 12.
Go ahead.
Yeah, so there's some trade-off there in it's complicating the arithmetization. Yes, yeah, so at the top of page 12.
How about I share my screen again so that we're all looking at the same. At the top of page 12.
Yeah. Yeah, I was just wondering if you could maybe go into a bit more detail about this construct, or where that trade-off comes about.
So what's the thing that is being looked up from the perspective of the hash coprocessor is actually not bytes, but pairs of bytes. And it looks these up in a table called the cascade table, which itself looks up bytes, single bytes, in the lookup table. The reason why this level of indirection is there is because every lookup is, well, it comes with a bunch of extra columns. And there are 4 columns, there are 4 field elements in the hash table that are being mapped by the split and lookup map. Every such field element consists of 8 bytes. So we would be looking at 32 lookups for every row of the hash table. But with this construction, we actually divide that number by 2 because we're only looking up pairs of bytes instead of bytes. So we have fewer columns in the hash table. We have fewer columns in total. Reason why you can't do this indefinitely, right? You might ask the question, why don't we cascade several times? Why don't we look up U32s, then pairs of bytes, and then bytes? And the reason why that doesn't work is because the number of rows in the cascade table grows. It grows faster than the number of rows in the hash processor. But there's a point at which the number of rows are saturated. You can never get more than 2 to the 16 rows in a lookup table of width 2 to the 16. And so we decided that's a good trade-off. We expect most of our programs will be more than 2 to the 16 cycles anyway. And so the cases in which this cascade table dominates, they're going to be so rare that it's just worth it doing it like so. On the other hand, if we were to look up U32s, then the first cascade table, the one that the hash table talks to, its number of rows would grow, and it doesn't saturate quite as quickly. And so there might be a point where 2 to the 32 would be or where the number of rows approaches 2 to the 32, which is obviously infeasible. Does that answer the question?
Yeah, that's great. Thanks.
So at a slightly higher level, it seems to me that the use of lookup tables in hash function is pretty recent. Do you think that there are any potential vulnerabilities, any reason to think that this might not be safe?
I don't. I think lookup tables are a robust security enhancement relative to the much more arithmetizable hash functions that you can build if you just use addition and multiplication, like Poseidon and Rescue. Lookup tables make a whole range of algebraic attacks infeasible. Do they introduce vulnerabilities? I would say no, but no in general. It depends on the particular lookup table and the particulars of the remainder of the construction. I'm sure you can find a construction where if you swap out a power map with a lookup with a particular lookup table, then you get something insecure. And so the paper actually raises a number of questions that you might want to consider, like, does the lookup map come with linear approximations? Here we go. Because if there are good linear approximations, then you might be able to apply an algebraic attack anyway and pray that the algebraic solutions that you find actually correspond with the good points where the approximation is accurate. Yeah, so long story short, there is no silver bullet. You have to do the analysis, but in general, I think lookup gates are a robust way to get security. They give you security at a cheap cost in terms of CPU performance, but it is rather expensive in terms of arithmetization.
Cool, thanks.
Alan, don't you sort of mention that I mean, there's been a lot of uses of lookup gates in other hash functions. It's just that there weren't proof arguments.
Yeah, the reason why arithmetic hash functions with lookup gates are new is because the arithmetic arguments for doing lookups are relatively new. Yeah, that's it.
So yeah, so I mean, there's been like kind of established sort of cryptanalytical approaches to lookup gates in other hash functions, or not?
Lookup gates are not very dissimilar from gates. We treat gates as a black box, and we analyze the input-output behavior. And maybe a black box is not the right analogy, but yeah, the standard methodology for analyzing the security of hash functions and symmetric ciphers applies to any kind of gate, whether it's a lookup gate or something more arithmetizable. And in fact, you could say that the S box in AES is arithmetizable because it's defined over the finite field with 2 to the 2 to the 8 elements. Or you could say it's a lookup gate because the fastest way to compute it is just to store an array of input-output pairs. So the distinction becomes blurry.
Okay, thanks. Also, sorry, why is it you mentioned you were getting greater speed ups than you'd calculated, or that the paper mentions in your implementation?
I actually don't know. So I can tell you why there isn't an apples-to-apples comparison, and that has to do with the previous hash function rescue prime had 8 rows per hash function invocation, 8 rounds per permutation, and Tip5 has 6, right? Because there are 5 rounds and you need to collect the state before and after. And for the program that we were using to benchmark, that actually makes the difference as to whether you need to blow up to the next factor of 2, power of 2. And so the number of rows that we get for the entire execution trace on our benchmark program for Tip5 was smaller. So it's not a fair comparison, but that number was very positive in favor of Tip5. And I guess if this paper gets published, and then we'll have to plug some more concrete numbers to that, and so we'll make sure to have a proper apples-to-apples benchmark. But for the time being, we are happy with the numbers that we have.
You just mentioned while commenting on reinforced concrete that you like your hash functions to have like a uniform round structure. Is this based on a heuristic of, non-uniform rounds expanding the attack surface, or is there something else?
There are two things. One is it's not so much non-uniform rounds that might expand the attack surface. It's all the difficulty against all the what is it? All the points where that make an algebraic attack difficult against reinforced concrete are localized within one round. All the rest is easy to attack, and that strikes me as putting all your eggs in one basket. I could live with a non-uniform round structure, but this is too far from uniform to make me happy. And the second argument is it's difficult to arithmetize something like that in a Stark. You want, I mean, you can have alternating rows. What is it? Constraints that apply in alternating rows. That's not too difficult, but a constraint that applies in one row out of every 16 or what number have you, that's cumbersome.
Yeah, that's a good point.
Also, because you designed this for such a specific usage, do you see that there's much room for improvement, like in this use case?
Well, I certainly think that it's very not obvious how to adapt this hash function to other fields. It's very specific to a field, and yeah, if you like the construction, it's anyone's guess how to adapt it to another field. Can you hang on? Can you repeat the question, because I'm not sure I answered it completely.
I meant, yeah, more that because yeah, but the design goals were so specific and for a specific field, whether how you can see some improvement in this particular construct. Yeah, because it seems to me it's been very optimized for such a specific use,
Yes. So here's one possible optimization. We found that for our code base, representing all field elements in Montgomery form gives the fastest arithmetic. So the hash function is actually geared to that, in that before splitting the field element into bytes and after recomposing it, you multiply by, what is it, the element that is congruent to 2 to the 64, or you divide by it. And you can drop that step if you're not working in Montgomery form. It does not affect security. We are targeting 160 bits of security. And so if you don't need quite that many bits of security, you can consider reducing the number of field elements or just outputting fewer of them as the hash digest. What else can you do? A significant amount of effort has been put, and we continue to put into optimizing the MDS matrix multiplication procedure. The algorithm that I sketched is really only the bare surface. And then you can throw single instruction, multiple data intrinsics at it, and I'm sure that will give rise to improvements also, but I guess those are not mathematical improvements anymore.
Okay, do we have any other questions? Alan? Okay, looks like not. So I'd just like to thank you for joining us again, Alan. Really,
Sure.
really interesting talk and paper. Did you say it hasn't? You haven't submitted it for publication?
We did submit it actually, but that was before we were expecting it to be accepted. And in the meantime, it's undergone several revisions. So if the reviewers would have to make a decision, they would have to make it on an old version of the paper, and yeah, who knows? But yeah, I think it's a good paper, and I think it makes sense to push for publication somewhere other than ePrint. But yeah, simultaneously, it takes a lot of effort to put a paper into pristine state for publication, and maybe other tasks have priority over that. So we'll see. All right, let me stop the recording here.